prime divisor on Cu, I can take its closure in CT. Maybe this is becoming a little bit obscure in the corner of the board, so I'll just give myself a bit more space. So here's my TCT, TU or UT or something, whatever it's called. And on here I have my divisor, say DI. And what I do is I just take its heuristic closure. And so you can easily check that this thing stays a Weil divisor, so the dimension stuff all works out fine. This is a Weil divisor, but because C is assumed to be regular and T and the map from T to S is smooth, I know that actually CT is also regular. So if I take a regular thing and I pull back along a smooth map, it stays regular. So this is regular because T over S is smooth. But if I have a Weil divisor on a regular scheme, then I know that it's a Cartier divisor. Okay, so this thing is a Cartier divisor, and so I can write O of it, sort of, well, it's safe to write O of it and have that be a line bundle. And so this L bar, which this is OCT, this is OCU, this L bar is a line bundle on CT, which extend, and certainly its restriction to CTU is just this thing. I mean, I defined it by taking zero-scheme closures, so it must have been that I started. So I define this line bundle L bar, and then, well, L bar will, so to give a, I've now given a line bundle on CT. Giving a line bundle on CT is exactly defining a map from T to pick, and then from T to Q. So L bar on CT, this gives me a map from T to pick. From T to pick, you have to check that it actually lands in the degree 0 bit, but this is very easy. And then I can compose with my map to Q. And this is the composite that I wanted. Okay. Wonderful. So if we can prove the closure of the unit section is flat, then we get that we have a narrow model. So our previous goal was to prove theorem 2, so our new goal is then to prove theorem 3. Okay, so at this point we can make sort of a convenient simplification. We can assume that our S is a strictly Henselian local scheme, so it's the spectrum of a strictly Henselian local ring. So you can't really do that for proving the existence of narrow models because we don't understand very well how narrow models spread out. So if you have a narrow model over the sort of Zariski local ring, we don't know that there's an open neighborhood on which it is a narrow model. This is very annoying. On the other hand, to check that something is flat, you can certainly check that over local rings. So like for this theorem 3, we can make the simplifying assumption that S is strictly Henselian local. So we can assume S is strictly Henselian local. And equivalently, all finite-tile things, well, not equivalently, all finite-tile things over S are actually just unions of copies of S. So this is makes life rather easier. Okay. So what does this E look like? So it comes to map to S. This is an isomorphism over U. Okay, over U our curve is smooth, and so the Jacobian is just an abelian scheme. In particular, it's separated, so the closure of the unit section is just the unit section. So the projection map, this is so over U. This is just the map from the unit section projecting down to the base again. So it's certainly an isomorphism. If you like, you can think of this as being a birational map. And also, do I do this? Oh, right. Oh yeah, we do this. And so, well, we defined E by taking the closure of the unit section, and so we can check very easily that this sort of EU bit, this is dense in E. I mean, basically defined by we defined E to be the closure of EU. Here I've written schematically dense instead, and that's because if one takes closure of things, one has to worry what one means about reduced structure. So when I say take the closure, what I should more formally say is take the schematic image, and then by definition, the thing of which we took the schematic image is schematically dense. But if you're not familiar with these things, then just think of it as dense, and then don't worry too much about the reduced structure. So we're just saying this EU is dense. And it's locally of finite type, equivalently finite representation, but it's not quasi-compact in general. It's almost never, it's quasi-compact if and only if the curve is actually all the sides of it irreducible. So locally of finite type is not too bad, because that just follows, we know the same thing for pick. We know that pick is locally of finite type, and then some closed thing in Rover and Ethereum base, everything is fine. So this is going to be locally of finite type. But it's not quasi-compact, it's going to have infinitely many, it sort of looks like infinitely many leaves. You take a big infinite pile of leaves and then you glue them together over U, but you still have all of these sheets surviving over the middle somehow. I guess the first example you see of a non-separated scheme is, right, US is not separated. So the classic example of a non-separated scheme is you take the affine line with a double origin. And here this is something like taking the affine line with infinitely many origins. Only of course it's also of high dimension. So it's a slightly weird thing. What we're trying to prove is that this thing is flat, of course. So we don't know that. I mean, it's not in general true. So supposing we have a map satisfying these conditions, so it's somehow birational and locally of finite type, but it's maybe not separated, what can it look like? So notice that, if, so let's have a lemma. So this is really a lemma about E, but I'm going to state it slightly more generally, because why not? So let's have f from x to s be an isomorphism over U, and such that x u to x is schematically dense, and f is locally of finite type. So basically, we're in this situation. Then the following are equivalent. F is étale. 2 says f is flat. Okay, so, well, 1 implies 2, I'll leave to the reader. So the third one is the fun of the useful one for us really. It says that every point upstairs has a section going through it. So here's my S and here's my mysterious X. Well, it doesn't look very birational either. And so if I take this is my little X, it tells me I can find a section going through it. So let's prove this lemma and then have our break. So remember that scheme S is strictly Henselian local to make life easier. And so things which are étale over S, so being étale over S and being separated is just being like a union of open subsets of S.
Sorry? If I take X F to be the open immersion of U inside S, then I get a problem in the number 3. Like number
yes. You're completely right. What I want to say, there's a section. Thank you. Just. So Vx, S open, and sigma. So I better restrict with the group. Does that help? Are you still worried?
You want to go to X, right?
Oh,
from V to X.
yes, thank you. So you no longer have a counterexample? Yeah, so the problem, so what I wrote down was previously false. The counterexample was given by the inclusion of an open subset into S, which is certainly étale and flat, but it doesn't have a section. So what I said was certainly not true. So what I should say is sort of locally there is a section through S. Okay. Okay, so remembering our S's, so somehow this is our S. Now we can all, like, if we believe this lemma, then if this thing is flat, it really just looks like sort of a bunch of copies of this thing. The drawing is terrible. Except that we are allowing them sort of to be, like over U, we glue these sheets together, but over those points we don't glue them together. So proof 1 implies 2 is obvious. 2 implies 3. So this is sort of slightly plagiarizing or copying an argument of Luc Beaumont in his paper on compactification of schemes. But in the end, the argument is not really like this. But anyway. So okay. So we're assuming to start with that F is flat, but we can shrink things a bit to be basically flat. In other words, flat and surjective. So we're like, it's flat and locally finite presentation, so it's open, so just replace S by the image of F. We can also assume that it's of finite type. So in other words, I mean, we already use locally finite type, so you could equivalently write quasi-compact here. So just replace X by some open neighborhood of the point that we care about. And we can assume that X and S are affine. So the shrinking is really a really good operation. We can just replace this by open neighborhoods of things. So we can assume X and S are affine. You have to be slightly careful about the order you apply these things in. Otherwise, like when you do one, you break the other one. But if, as long as you're slightly careful here, it all works out. Okay. And so in particular, F is separated. Now, if X and S are both affine, then certainly F is separated. So then I claim then F is an isomorphism. Well, if it's an isomorphism, so basically what I'm saying is after replacing X and S by small open subsets, the map actually becomes an isomorphism, and then I can just define my section to be the inverse of the isomorphism and I win. So yeah, being an isomorphism looks much stronger than having a section, but it's also actually a much easier property to work with because being an isomorphism is stable under that satisfies FPPF descent. So if I know that it is an isomorphism after making some FPPF base change, I know that it was an isomorphism before. Moreover, I have a natural choice of morphism along which, facially flat finite kinetic morphism, along which to make my base change. So I'm going to, so now to check this, after some FPPF base change, so let's base change along S. So along F. So it's the only thing, I mean, we have to choose something at FPPF, and that's the only thing we've got around, so let's do that. So then we have a section. So I have my but then this has a section which is given by the diagonal. So now I can reduce myself to the case where all of these things are true, and moreover, my map has a section. Grand. This is like, okay. This is a sort of weird argument because you might think, oh, we have a section, that's what we wanted. But that's not really good enough because having a section isn't something you can check FPPF locally. So we really need to push a little bit further and check we have an isomorphism. But actually, so then delta and Fx are mutual inverses because they are on semantically dense opens and everything is separated. Okay, so there's a lemma, maybe you've seen the version in U or Hartram or something, which says that if I have two maps, say I have two maps F and G from X to Y, and suppose they agree on some dense open, and the target, so the source is reduced and the target is separated, and they agree on a dense open, then the maps are actually the same. So this is sort of maybe this is actually worth writing down. So the standard version that you're likely to have seen is F and G, and we're going to assume that F restricted to U is equal to G restricted to U for some U contained in X dense open, and that X is reduced and Y is separated, then F equals G. This is some standard lemma that we're all supposed to remember. So that's basically what I'm using here, except I'm using a sort of slightly more funky version. So what I'm doing, instead of assuming that U is dense and that X is reduced, I'm assuming that U is schematically dense. And then that is enough, it turns out. And then when you come down to actually try to prove this, you realize that you've basically just rewritten the definition of schematic density. So at some point the argument becomes almost circular, but so it goes. Okay. So we find that these maps are actually mutual inverses. So we win. So let's do 2 implies 3 implies 1. And it's almost the same argument again, so I'll just do the beginning again instead as before. So 3 implies 1, we want to show that F is a tile again. Shrink such that F is separated. Then we have a section type. I don't think I actually even used the finite types. So, well, I said they're affine. So basically, after you with a shrink, I can sort of do all the same kind of shrinking again, but instead of getting faithfully flat, I already have a section. Oh. And we have a section by assumption. Again, one has to be a little bit careful about the order in which you do the shrinking so that your section from part 3 survives. So then I'll use as before. And isomorphism. So you just sort of, you put yourself back into this situation where you have a section, and then you just repeat this little argument and you find that it's actually an isomorphism. Okay. So locally it's an isomorphism, so certainly it's a tile. Awesome. So this seems like a good point to stop and have our drink.